Okay, let's continue. Number 9, c to the fourth plus c to the third minus c to the second minus c. On this particular polynomial, we are going to use a method known as factoring by grouping. If we put parentheses around the first two terms and parentheses around the second two terms, noticing there that I changed that third term to plus a negative c squared. Now what we go ahead and do is factor out if there exists a GCF out of the first two, but then also the second two. Between c to the fourth and c to the third, there is a GCF of c to the third. In the event that then you divide out that c to the third, c to the fourth divided by c to the third, you get c to the third divided by c to the third, 1. And then on the second two terms, we can see that there's a GCF of c. Now technically I'm going to factor out a negative c, so that watch, when you factor that out, you are left with, well, negative c squared divided by negative c, a positive c. Negative c divided by negative c, positive 1. Now what you have here, as you see in the parentheses, c plus 1 and c plus 1, those are the same binomials there, where we can then factor that out. Because they're the same, factor it out, and then we are left with c to the third minus c, and that stems from these two terms. Okay, now we're not done. There is one last step here to identify here with, and that is noticing that there is a GCF between these two terms. So I have c plus 1 times c, which I factor out, times the quantity c squared minus 1. And then with that, we can continue with one last step, factoring c squared minus 1, because it is the difference of two squares. So c times the quantity c plus 1, and then c plus 1, c minus 1, the result of factoring c squared minus 1. That, right there in full, is your final answer. So there are 1, 2, 3, 4 factors of this particular quartic. On to the next page. So solving polynomial equations. If a polynomial expression can be written in quadratic form, then you can use what you know about solving quadratic equations to solve the related polynomial equation. Example 1. Solve x to the fourth minus 40x squared plus 144 equals 0. So our original equation has three terms. Now, as you see here, the steps indicate to write the expression on the left in quadratic form. This is actually a pretty important step with regard to then identifying that quadratic as one that you're more familiar with in the factorization. So x squared squared x to the fourth. X squared in parentheses, and then we'll still plus 144, no change on that term. And that then leads to the following: x squared minus 4, x squared minus 36. Another way to interpret this is to use a substitute for, in this case, x to the second. This is called u substitution. So what we can do, taking u, substituting it in for x squared, is rewrite the problem as follows. We can write u squared minus 40u, because again, that's what x squared is equal to, and then plus 144 equals 0. Okay, so this is definitively a quadratic, albeit a different variable. However, though, we can factor this. As you'll see on the step using x off to the side here, I'm going to go ahead and continue, though, using u. So u times u, that's u squared. And then we want to think, okay, two numbers that multiply to positive 144 and add to negative 40. Well, we can see that negative 4 and negative 36, as we see off to the side there, are those two numbers. Negative 4 times negative 36 is 144. Negative 4 minus 36 is negative 40. Now we're not done. What we then do is take what we substituted in the first place for x squared. We substituted u, but now we go back and plug x squared in for u. And this is the quadratic that we are ultimately going to want to continue with. And that's where you see the work here. X squared minus 4 times x squared minus 36 equals 0. So what is done then is, well, take the x squared minus 4, set that equal to 0. Take the x squared minus 36, set that equal to 0. Leaving you then with a factored form of x plus 2, x minus 2 equals 0. X plus 6, x minus 6 equals 0. So there's truly 1, 2, 3, 4 factors, of which then you set equal to 0. X minus 2 equals 0, therefore x equals 2. Same with x equals negative 2, same process. X equals 6, and x equals negative 6. So your full final answers here are plus or minus 2 and plus or minus 6. So this is taking those factoring steps and now solving by setting your factors equal to 0. Example 2. Solve 2x plus the square root of x minus 15 equals 0. So again, we've got ourselves a trinomial, albeit though not a quadratic. But if we go ahead and rewrite this problem similar to the last in that, well, we're going to identify with a quadratic, one that I will again attempt to use u substitution. So this time I'm going to actually let u equal the square root of x. So then if I rewrite my original problem, instead of using square root of x, I'll use u. So I've got 2 u squared. Because if I were to square both sides of this equation, I'd have x squared equals, or excuse me, u squared equals x. So 2u squared plus u minus 15 equals 0. Okay, there's a good chance that this is factorable. As it turns out, two numbers that multiply to 2, well, 2 and 1, so 2u and 1u. And then we can play around with the values for negative 15, knowing that we can use 3 times 5, or switch it 5 times 3, 1 times 15, or 15 times 1. But also the signs, of course, can either be positive, negative, or both positive, both negative. 3 and 5 appear to be the best solutions in those particular spots, but also negative 5, positive 3. Those signs appear to be the best as well. So if we FOIL this, we'll get 2u squared, 6u, negative 5u, and negative 15. The outside and inside are needing to be combined, so 6u minus 5u is 1u, and negative 5 times 3, of course, negative 15. So that works. So just like the last problem, we'll go back and put a radical x in for u so that it looks like the original problem in that it has the variable x and not u. And there's our factored form, as you see in the step over here to the left. So that is factored appropriately. And the next step, it's as easy as taking that factor, setting it equal to 0, taking this factor, setting that equal to 0, divide by 2, actually add 5 first, then divide by 2. So the square root of x equals 5 halves. Subtract 3, square root of x equals negative 3. Now the next step, and I'll stick with this here, is to square both sides. And the point of that is, of course, to get x by itself. So what we then have is x equals 5 squared, which is 25, 2 squared, which is 4. So there's one solution. And then the square root of x squared, well, that's x again, but negative 3 quantity squared. Well, they say it has no solution. So 25 fourths, or 6 1/4, is the solution. But I want to speak briefly about why this is the case. Okay. In other words, when you square both sides, 9 may have entered into the picture. You may have thought of using 9. But what happens when you plug it in? And truly you need to plug in both of your answers to see if it works. But let's just test 9 and see if in fact this works. So we have 2, this is the original problem, times 9 plus square root of 9 minus 15. So if we do our math, and by the way this is equal to 0, okay, we've got 18, 2 times 9 plus 3 square root of 9 minus 15. Does that equal 0? Well, we've got 18 plus 3, 21 minus 15. Well, of course, that is not equal to 0. 6 is not equal to 0. So we do say that this answer doesn't actually work. Okay, so it is important that we check our answers when we do square root problems. It would be imperative to check 25/4 as well. The way that I'm going to check that is actually using the calculator. We've done this before with our store feature. So I'll take 25/4, store that as x, and then I'll go ahead and type in the original problem. The original problem was 2x plus square root x minus 15. Put parentheses. For my calculator it won't be necessary because I can see that I can differentiate easily. And then minus 15. But just be careful with the TI-83, you may have to use parentheses. Now if this is a correct answer, I should get 0. And I do. Okay, so there's no question that 25/4 is in fact a solution. Okay, on to the exercises. Okay, so we're going to do a couple here. The first one, truly not too bad. X to the 4th equals 49. I'm going to subtract 49 first. Set this equal to 0. From here, I can go ahead and see if factoring is plausible. It is, because, well, 49 is a perfect square, and x to the 4th is a perfect square squared. It's actually a perfect 4th. But as it turns out, in our factoring, I can rewrite x to the 4th, break it down as x squared and x squared. I can take, of course, 49 and write that as 7 times 7. And because it is actually the difference of 2 perfect squares, of course, this again being a squared squared term, it becomes plus and minus. And that's truly it as far as factoring. When it comes to solving, though, of course, we've got to set this equal to 0. So x squared plus 7 equals 0. X squared minus 7 equals 0, which then I'll end up with x squared equals negative 7. X squared equals positive 7. Take the square root of this. Take the square root of this. So 2 separate equations require the same process. X therefore equals, now because I have a negative and I'm taking the square root of that, I have to consider what we looked at back in a previous chapter, the square root of 7 and then I, because it is negative. And for this respective equation, I'll take x equals plus or minus simply root 7. I can't do anything further to either equation. My final answer is plus or minus root 7i, but also plus or minus root 7. Okay. On to number 3. Number 3 is a quartic that's not set equal to 0. So I'm going to get everything on one side and set the equation equal to 0. This is another quadratic type of problem. It's raised to the 4th, but I'm going to go ahead and start the process. Similar to what I saw in the example, I'm going to go ahead and rewrite x to the 4th as x squared times x squared. And I need to think, okay, what two numbers multiply to negative 54 and add to negative 3? 9 and 6 should do the trick. Because my negative 3 is the middle coefficient, I'll make this negative, make this positive, and we can continue by factoring.